Good evening and welcome. As you settle into rest, allow your breathing to slow and your thoughts to soften. Tonight, we will move gently into the microscopic foundations of the physical world, not into mystery and not into speculation, but into structure, into the quiet framework that underlies everything you touch, see, and experience. The microscopic world is not chaotic. It is governed by stable principles. It follows mathematical laws. Its behavior has been measured, tested, and described with remarkable precision. Every solid object, every liquid, every gas, and every living system is built from the same consistent rules, operating at scales far smaller than the eye can see. These processes continue constantly and reliably. They do not pause. They do not fluctuate unpredictably. They form the steady architecture of matter itself. If you find this exploration calming and would like to return to it again, you may consider subscribing. For now, simply rest, and we begin. Atoms are the fundamental structural units of ordinary matter. Every material object around you is composed of atoms. An atom is the smallest unit of a chemical element that retains that element's properties. While atoms are extremely small, on the order of 1/10,000,000,000th of a meter in diameter, they are not indivisible. They have internal structure. They consist of a dense central region and a surrounding distribution of electrons. Atoms combine with one another in consistent and predictable ways. The properties of metals, gases, minerals, and biological molecules all arise from how atoms are arranged and how they interact. Although invisible to the naked eye, atoms form the stable building blocks of the visible world. At the center of every atom lies a compact nucleus. The nucleus occupies only a tiny fraction of the atom's total volume. Yet, it contains nearly all of the atom's mass. Its diameter is roughly 100,000 times smaller than the overall size of the atom. Despite this small size, it is extraordinarily dense. The nucleus is composed of two types of particles: protons and neutrons. These particles are packed closely together by powerful forces. The stability of matter depends critically on the integrity of this compact core. Without the nucleus, atoms would not exist in a stable form. Protons carry positive electric charge. Each proton possesses a charge equal in magnitude, but opposite in sign to that of an electron. This positive charge defines the identity of an element. The number of protons in the nucleus is known as the atomic number. Hydrogen has 1 proton, carbon has 6, oxygen has 8, gold has 79. Changing the number of protons changes the element entirely. This is not a small adjustment. It alters the entire chemical behavior of the atom. The periodic table is organized according to increasing numbers of protons. In this way, the positive charge of protons anchors the structure of chemistry. Neutrons contribute mass but carry no electric charge. Neutrons reside alongside protons within the nucleus. Although electrically neutral, they are essential to nuclear stability. They help offset the repulsive force between positively charged protons. Without neutrons, many nuclei would not remain intact. Different atoms of the same element can contain different numbers of neutrons. These variants are called isotopes. For example, carbon-12 and carbon-14 both contain 6 protons, but they differ in neutron number. The chemical behavior remains largely the same because chemical identity depends on protons. However, nuclear stability may differ. Electrons occupy regions surrounding the nucleus. Electrons are much lighter than protons and neutrons. Their mass is approximately 1/1800th that of a proton. They carry negative electric charge. Instead of orbiting the nucleus in simple circular paths, electrons exist in regions described by quantum mechanics. These regions are often called orbitals. An orbital does not describe a fixed path. It describes a probability distribution. It defines where an electron is likely to be found when measured. This probabilistic description does not indicate randomness in the everyday sense. It reflects the mathematical structure of quantum theory. The atom is mostly empty space. If the nucleus were enlarged to the size of a small marble, the surrounding electrons would be distributed across a region roughly the size of a large stadium. The mass would remain concentrated in the central marble. The surrounding space would be largely unoccupied. This empty space does not imply instability. The atom remains stable because electromagnetic forces hold electrons in bound states around the nucleus. The apparent solidity of matter arises from interactions between electron distributions in neighboring atoms, not from densely packed mass throughout the atom. Electric charge governs interactions within atoms. Opposite charges attract. Like charges repel. The positively charged nucleus attracts negatively charged electrons. This attraction is described by the electromagnetic force. It follows precise mathematical laws, including Coulomb's law. The balance between the attractive pull of the nucleus and the quantum behavior of electrons produces stable atomic structures. Without this balance, electrons would either collapse into the nucleus or escape entirely. Instead, they occupy stable energy states determined by quantum mechanics. Electron energy levels are quantized. Electrons cannot possess arbitrary amounts of energy within an atom. They occupy discrete energy levels. Each level corresponds to a specific allowed energy value. These values arise naturally from solving the equations of quantum mechanics for an electron in the electric field of the nucleus. When an electron moves between energy levels, it absorbs or emits energy in precise amounts. This energy often appears as light with specific wavelengths. The characteristic spectral lines of elements arise from these quantized transitions. Spectroscopy has confirmed these predictions with high accuracy. Quantum mechanics describes electron behavior mathematically. The behavior of electrons is governed by the Schrödinger equation. This equation predicts how quantum systems evolve and what energy states are allowed. Solutions to this equation produce wave functions. A wave function encodes the probability distribution for locating a particle. The mathematical framework does not rely on visual imagery. It relies on precise equations. Experimental results consistently match predictions derived from this theory. The probabilistic aspect reflects measurement outcomes, not instability in physical law. At smaller scales, particles exhibit both wave-like and particle-like properties. Electrons can produce interference patterns, a behavior associated with waves. Yet they also deposit energy in discrete packets when detected, a behavior associated with particles. This dual aspect is described within quantum theory as wave-particle duality. The theory does not treat these as contradictory. Instead, it uses mathematical objects that account for both behaviors. The consistency between prediction and experiment reinforces the reliability of the framework. The microscopic world follows rules that are internally coherent and experimentally verified. Protons and neutrons are themselves composed of smaller particles. Within the nucleus, protons and neutrons are not elementary. Each consists of 3 quarks bound together by the strong nuclear force. Quarks are fundamental particles. They cannot be divided into smaller components according to current understanding. Protons contain 2 up quarks and 1 down quark. Neutrons contain 2 down quarks and 1 up quark. The arrangement of quarks determines the charge of the particle. Up quarks carry a positive fractional charge. Down quarks carry a negative fractional charge. Combined, they produce the observed charge of protons and neutrons. Quarks are held together by the strong nuclear force. The strong force is one of the 4 fundamental forces of nature. It operates at very short distances. It is mediated by particles called gluons. Gluons transmit the force between quarks. Unlike the electromagnetic force, the strong force becomes stronger as quarks are pulled apart. This property ensures that quarks remain confined within protons and neutrons. They do not exist freely under normal conditions. This confinement contributes to the stability of atomic nuclei. The 4 fundamental forces govern all microscopic interactions. These forces are the strong force, the electromagnetic force, the weak nuclear force, and gravity. At atomic and subatomic scales, gravity is negligible compared to the other 3. The electromagnetic force governs interactions between charged particles. The strong force binds quarks and holds nuclei together. The weak force enables certain forms of radioactive decay. Each force has been described mathematically within quantum field theory. Their strengths differ by many orders of magnitude. Yet together, they account for all known particle interactions observed in experiments. The weak nuclear force enables particle transformations. The weak force is responsible for processes in which one type of particle changes into another. For example, in beta decay, a neutron can transform into a proton while emitting an electron and an antineutrino. This process alters the composition of the nucleus. The weak force operates over extremely short distances. It is mediated by heavy particles known as W and Z bosons. Although less familiar than electromagnetic interactions, the weak force plays a critical role in nuclear stability and in processes within stars. The Standard Model organizes known fundamental particles. The Standard Model of particle physics classifies elementary particles into quarks, leptons, gauge bosons, and the Higgs boson. Quarks and leptons are matter particles. Gauge bosons mediate forces. The Higgs boson is associated with the mechanism by which particles acquire mass. This framework has been tested extensively in high-energy experiments. Particle accelerators, such as those at CERN, have confirmed many of its predictions with high precision. While not a complete theory of all physical phenomena, it remains one of the most successful scientific models developed to date. Leptons include electrons and neutrinos. Electrons are familiar components of atoms. Neutrinos are much lighter particles that interact only weakly with matter. Trillions of neutrinos pass through your body every second without noticeable effect. Their interaction probability is extremely low. Leptons are considered elementary. They are not composed of smaller constituents. Their properties, such as mass and charge, are fundamental parameters within the Standard Model. Their consistent behavior across experiments reinforces the stability of microscopic physics. Chemical bonding arises from electron interactions. Atoms combine to form molecules through the sharing or transfer of electrons. In covalent bonding, atoms share electron pairs. In ionic bonding, one atom transfers electrons to another, creating oppositely charged ions that attract. The shapes and strengths of these bonds are determined by quantum mechanical principles. Electron orbitals overlap in specific ways. Energy minimization governs the formation of stable molecular structures. These principles explain why water has its particular geometry, and why carbon forms complex organic frameworks. Molecules are stable arrangements of bonded atoms. A molecule forms when atoms are linked through chemical bonds into a defined structure. The properties of a molecule depend on the types of atoms involved and their arrangement. Water consists of 2 hydrogen atoms bonded to 1 oxygen atom in a bent geometry. This geometry influences physical properties such as boiling point, polarity, and hydrogen bonding behavior. Larger molecules, including proteins and DNA, rely on the same fundamental bonding principles. Complexity arises from repetition and arrangement, not from new physical laws. At the microscopic scale, temperature reflects particle motion. Temperature is a measure of the average kinetic energy of particles. In solids, atoms vibrate around fixed positions. In liquids, they move more freely while remaining close together. In gases, particles move independently across larger distances. These motions arise from energy distributions described statistically. The field of statistical mechanics connects microscopic particle motion to macroscopic quantities like pressure and temperature. The equations governing these relationships are well established and experimentally verified. Probability in quantum mechanics reflects measurement outcomes. When describing electron position, quantum mechanics provides a probability distribution. This distribution indicates the likelihood of detecting the particle at various locations. It does not imply that physical law is uncertain. It reflects how measurement interacts with quantum systems. Repeated experiments produce statistically consistent results. The probability patterns are stable and reproducible. The mathematical formalism accurately predicts these distributions. In this way, probability is integrated into the structure of physical description without undermining predictability at larger scales. Microscopic structure determines macroscopic properties. The hardness of diamond arises from a rigid lattice of carbon atoms bonded in a 3-dimensional network. The softness of graphite arises from layers of carbon atoms bonded strongly within layers but weakly between layers. Both are composed of the same element. Electrical conductivity in metals arises from delocalized electrons that move through a lattice of positive ions. Insulators lack this freedom of electron motion. These differences are consequences of atomic arrangement and bonding, not separate physical laws. The microscopic world forms a consistent foundation for visible matter. Every surface, every object, and every biological structure depends on atomic interactions governed by electromagnetic and nuclear forces. These forces operate continuously and reliably. They do not fluctuate unpredictably at human scales. As we continue, we will move gradually deeper into how these interactions shape materials, how quantum fields describe particles, and how stable mathematical laws govern even the smallest scales of reality. The structure remains steady. The rules remain consistent. The microscopic world continues quietly, forming the stable architecture beneath everything around you. Electron orbitals define the spatial structure of atoms. An orbital is a solution to the Schrödinger equation for an electron bound to a nucleus. Each solution corresponds to a specific energy and a characteristic spatial distribution. These distributions are not arbitrary. They are determined by boundary conditions and by the electric potential created by the nucleus. Orbitals are labeled by quantum numbers. These numbers specify properties such as energy level, angular momentum, and orientation in space. The simplest orbital, known as the 1s orbital, has a spherical distribution. Higher orbitals, such as p and d orbitals, possess more complex shapes that influence how atoms bond. The allowed shapes and energies of orbitals arise directly from mathematical constraints. They are not chosen by convention. They emerge from solving well-defined equations that describe electron behavior under electromagnetic interaction. Quantum numbers categorize electron states precisely. Each electron in an atom is described by 4 quantum numbers. The principal quantum number determines the energy level and average distance from the nucleus. The angular momentum quantum number determines the shape of the orbital. The magnetic quantum number determines spatial orientation. The spin quantum number describes intrinsic angular momentum. These quantum numbers are discrete. They can only take specific values. This discreteness ensures that electron configurations follow predictable patterns. It also explains the regular structure of the periodic table. No 2 electrons in an atom can share identical sets of quantum numbers. This principle, known as the Pauli exclusion principle, governs how electrons fill orbitals. It establishes order in atomic structure. Electron spin is an intrinsic property of electrons. Spin is not classical rotation. It is a quantum mechanical property that behaves mathematically like angular momentum. Each electron has spin equal to 1/2 in units defined by quantum theory. This allows 2 possible spin states. Spin influences magnetic behavior and atomic structure. When 2 electrons occupy the same orbital, they must have opposite spins. This pairing reduces energy and contributes to atomic stability. Spin also underlies magnetic materials. In certain solids, electron spins align collectively, producing macroscopic magnetism. This behavior arises from quantum interactions at the microscopic scale. The periodic table reflects electron configuration patterns. Elements are arranged in order of increasing atomic number. However, the repeating patterns across rows and columns arise from how electrons fill orbitals. When a new electron shell begins to fill, chemical properties change in systematic ways. Elements in the same column share similar outer electron configurations. These outer electrons, known as valence electrons, determine chemical reactivity. For example, elements in the first column each have 1 valence electron, leading to similar bonding behavior. The periodic structure is therefore not arbitrary. It reflects quantum mechanical principles governing electron distribution. Chemistry is organized according to these stable underlying rules. Valence electrons control chemical interactions. The outermost electrons of an atom participate directly in bonding. Atoms tend to combine in ways that lower total energy. Often, this involves filling or emptying outer shells to achieve stable configurations. For example, sodium has 1 valence electron. Chlorine lacks 1 electron to complete its outer shell. When sodium transfers its valence electron to chlorine, both achieve stable arrangements. The resulting charged ions attract. forming an ionic bond. In covalent bonding, atoms share electrons to achieve similar stability. The shared electrons occupy orbitals that extend between nuclei. This sharing produces directional bonds that determine molecular shape. Molecular geometry follows from electron repulsion principles. Electron pairs repel each other due to their negative charge. In a molecule, electron pairs arrange themselves to minimize repulsion. This principle, often described through valence shell electron pair repulsion theory, predicts molecular shapes. For example, in water, two bonding pairs and two lone pairs of electrons surround the oxygen atom. The repulsion between these pairs leads to a bent molecular geometry, rather than a linear one. These shapes are not approximate guesses. They are supported by quantum mechanical calculations and confirmed by experimental measurement, including spectroscopy and diffraction methods. Intermolecular forces influence physical properties. In addition to chemical bonds within molecules, weaker forces operate between molecules. These include hydrogen bonding, dipole-dipole interactions, and dispersion forces. Hydrogen bonds arise when hydrogen atoms bonded to electronegative atoms interact with nearby lone electron pairs. This interaction explains the relatively high boiling point of water compared to similar molecules. Dispersion forces arise from temporary fluctuations in electron distribution. Even non-polar molecules experience these forces. Although individually weak, they collectively influence melting points, boiling points, and material states. These interactions are governed by electromagnetic principles at the microscopic level. Solids are defined by ordered atomic arrangements. In crystalline solids, atoms or molecules occupy regular, repeating positions in a lattice. The arrangement is determined by energy minimization and bonding constraints. The structure of the lattice influences mechanical and electrical properties. For example, in sodium chloride, positive and negative ions alternate in a cubic lattice. This arrangement maximizes attractive interactions and minimizes repulsive forces. The periodic structure of crystals can be analyzed through X-ray diffraction. This method reveals atomic spacing and symmetry with high precision. The predictable nature of crystal structures reflects consistent microscopic interactions. Metals conduct electricity through mobile electrons. In metallic solids, valence electrons are not confined to individual atoms. Instead, they occupy energy bands that extend across the lattice. These delocalized electrons can move under the influence of an electric field. This mobility enables electrical conductivity. When a voltage is applied, electrons drift through the lattice, while positive ion cores remain fixed. The band theory of solids explains why some materials conduct and others do not. The difference between conductors, semiconductors, and insulators arises from the structure of these energy bands. The presence or absence of available energy states determines electrical behavior. Semiconductors depend on controlled electron energy gaps. In semiconductors, the energy difference between occupied and unoccupied bands is small. Thermal energy or light can promote electrons across this gap. This creates mobile charge carriers that conduct electricity. Materials such as silicon exhibit this behavior. By introducing small amounts of impurities, known as doping, the electrical properties can be finely controlled. This principle underlies modern electronics. Transistors operate by manipulating these charge carriers. At their core, they rely on quantum mechanical principles governing electron energy states in solids. Statistical mechanics links microscopic motion to macroscopic behavior. At any given temperature, particles possess a range of energies described by probability distributions. The Maxwell-Boltzmann distribution describes classical particle speeds. Quantum statistics refine this description for systems of identical particles. Fermi-Dirac statistics apply to particles like electrons, which obey the Pauli exclusion principle. Bose-Einstein statistics apply to particles that can occupy the same state. These statistical frameworks explain phenomena such as electron behavior in metals and superfluidity. The connection between microscopic randomness and macroscopic stability emerges through large numbers. Although individual particles move unpredictably, aggregate behavior becomes highly regular. Quantum fields provide a deeper description of particles. In quantum field theory, particles are excitations of underlying fields. Each type of particle corresponds to a specific field that exists throughout space. For example, the electron field permeates all space. When it is excited at a location, an electron appears. This description unifies particles and forces within a consistent mathematical structure. Interactions occur through the exchange of field excitations. For the electromagnetic force, the mediating particle is the photon. The predictions of quantum field theory have been confirmed with remarkable precision, including measurements of particle properties to many decimal places. Photons mediate electromagnetic interactions. Photons are massless particles that carry electromagnetic energy. They are responsible for light and for the electromagnetic force between charged particles. When electrons interact, the force can be described as the exchange of virtual photons. Photons also exhibit quantized behavior. Light energy is transferred in discrete packets. The photoelectric effect demonstrates this property clearly. Experimental observations match the theoretical predictions of quantum electrodynamics. The electromagnetic force shapes atomic structure, chemical bonding, and material properties. Its influence extends from subatomic scales to everyday experiences of light and electricity. The Higgs field contributes to particle mass. According to the Standard Model, particles acquire mass through interaction with the Higgs field. This field has a non-zero value throughout space. Particles interacting with it experience resistance that manifests as mass. The Higgs boson is the quantized excitation of this field. Its discovery at the Large Hadron Collider in 2012 confirmed a central prediction of the Standard Model. Mass determines how particles respond to forces and how they contribute to atomic structure. The presence of mass allows matter to form stable bound systems. Neutrinos demonstrate weak interaction behavior. Neutrinos are extremely light particles that interact only through the weak force and gravity. They rarely interact with matter. Large detectors buried deep underground are required to observe them. Neutrinos can change type as they travel, a phenomenon known as neutrino oscillation. This behavior implies that neutrinos have mass, although very small. Their consistent detection in experiments provides additional confirmation of weak interaction theory. Even rarely interacting particles follow predictable physical laws. The stability of matter arises from balanced forces. Within atoms, electromagnetic attraction balances quantum mechanical motion. Within nuclei, the strong force binds quarks and nucleons. despite electromagnetic repulsion between protons. These balances are not fragile. They are robust across a wide range of conditions. Matter remains stable under ordinary temperatures and pressures. Only extreme environments, such as stellar interiors, alter these structures significantly. The persistence of matter over billions of years reflects the reliability of these microscopic principles. Chemical reactions involve energy redistribution. When atoms rearrange into new molecular configurations, bonds are broken and formed. Energy is absorbed or released depending on relative bond strengths. Exothermic reactions release energy. Endothermic reactions absorb energy. These processes are governed by conservation laws. Energy and charge remain conserved. Reaction rates depend on temperature, concentration, and activation energy barriers. Catalysts can lower activation energy by providing alternative pathways. The fundamental forces remain the same. Only the arrangement of atoms changes. Conservation laws structure microscopic processes. Charge is conserved in all known interactions. Energy and momentum are conserved. These principles arise from symmetries in physical law, described mathematically by Noether's theorem. Symmetry under time translation leads to energy conservation. Symmetry under spatial translation leads to momentum conservation. These relationships apply from particle interactions to planetary motion. The stability and predictability of the microscopic world are rooted in these conservation principles. They constrain what can occur and ensure consistent outcomes. The microscopic world operates continuously and quietly. At every moment, atoms vibrate. Electrons occupy defined probability distributions. Photons travel between charged particles. Molecules form and break in living cells. These processes do not require observation to proceed. They follow mathematical laws independent of human awareness. Their scale is small, but their consistency is absolute. As we continue, we will move further into how these microscopic principles give rise to complex structures and how collective behavior emerges from atomic interactions. The structure remains precise. The rules remain intact. The microscopic foundation of reality continues steadily beneath the surface of the visible world. Quantum tunneling allows particles to cross energy barriers without classical trajectories. In classical physics, a particle lacking sufficient energy cannot cross a barrier. In quantum mechanics, the wave function describing a particle extends into classically forbidden regions. If the barrier is thin enough, there is a finite probability that the particle will be detected on the other side. This behavior arises directly from the mathematical form of the Schrödinger equation. The wave function does not abruptly vanish at a barrier. Instead, it decays exponentially within it. The probability of transmission depends on barrier width and height. Quantum tunneling is not speculative. It is measured experimentally. It explains phenomena such as nuclear fusion in stars and the operation of scanning tunneling microscopes. The effect is small at large scales, but significant at atomic distances. The uncertainty principle defines limits on simultaneous measurement precision. The Heisenberg uncertainty principle states that certain pairs of physical quantities cannot both be specified with arbitrary precision. Position and momentum are one such pair. The more precisely position is known, the less precisely momentum can be determined. This principle does not arise from measurement error. It follows from the mathematical structure of quantum states. Position and momentum are represented by operators that do not commute. This non-commutation leads directly to the uncertainty relation. The uncertainty principle sets quantitative bounds. It does not imply disorder. Instead, it defines a consistent limitation embedded within the formalism of quantum theory. Quantum superposition allows multiple possible states to coexist mathematically. A quantum system can be described as a combination of multiple possible states simultaneously. This superposition evolves deterministically according to the Schrödinger equation. Only when a measurement occurs does the system yield a specific outcome. The mathematical structure of superposition allows interference effects. These effects are observed in experiments such as the double-slit experiment with electrons and photons. The interference pattern reflects the coherent combination of probability amplitudes. Superposition does not imply ambiguity in the physical law. The evolution of the wave function remains precisely governed by equations. The probabilistic aspect emerges only in measurement outcomes. Wave functions evolve smoothly over time. The time-dependent Schrödinger equation describes how the wave function changes. This evolution is continuous and deterministic. Given an initial state, the equation predicts its future form exactly. The evolution conserves total probability. The mathematical framework ensures that probabilities remain normalized. This internal consistency reinforces the stability of the theory. In this sense, quantum mechanics provides a complete description of system evolution between measurements. The mathematical continuity ensures predictable behavior at the microscopic level. Atomic emission and absorption spectra reveal quantized energy levels. When electrons transition between energy levels, atoms emit or absorb photons with precise energies. These energies correspond to differences between allowed quantum states. Each element produces a characteristic spectrum. Spectroscopy allows scientists to identify elements in distant stars by analyzing light. The presence of hydrogen, helium, and heavier elements has been confirmed through this method. The discrete nature of spectral lines provides strong evidence for quantized energy levels. These observations align exactly with theoretical predictions derived from quantum mechanics. Plasma represents a state of matter where electrons are no longer bound to nuclei. At sufficiently high temperatures, atoms can become ionized. Electrons gain enough energy to escape from atomic orbitals. The resulting mixture of free electrons and positive ions forms plasma. Plasma behaves differently from solids, liquids, and gases. It conducts electricity and responds strongly to magnetic fields. The behavior of plasma is governed by electromagnetic forces acting on charged particles. Most visible matter in the universe, including stars, exists in plasma form. Yet the same fundamental forces apply. The underlying microscopic principles remain consistent. In stars, nuclear fusion combines light nuclei into heavier ones. Within stellar cores, temperatures and pressures are extremely high. Under these conditions, hydrogen nuclei can overcome electrostatic repulsion and fuse to form helium. Quantum tunneling contributes to this process. Fusion releases energy because the combined nucleus has slightly less mass than the sum of its parts. This mass difference is converted into energy according to Einstein's relation between mass and energy. The energy produced by fusion powers stars and ultimately supports life on planets. Yet the mechanism is entirely grounded in nuclear physics and quantum principles. Mass and energy are equivalent physical quantities. Einstein's equation, E equals mc squared, states that mass can be viewed as a concentrated form of energy. This relationship has been confirmed through nuclear reactions and particle experiments. In nuclear fission and fusion, small amounts of mass are converted into large amounts of energy. The conversion factor involves the speed of light squared, a very large number. This equivalence does not disrupt atomic stability under ordinary conditions. It becomes significant only in high-energy processes, such as those in stars or reactors. Entropy measures the number of microscopic configurations consistent with a system's state. In thermodynamics, entropy quantifies disorder at the microscopic level. More precisely, it measures how many microscopic arrangements correspond to a given macroscopic state. A gas spread evenly in a container has higher entropy than gas confined to one corner because many more microscopic arrangements correspond to uniform distribution. The second law of thermodynamics states that entropy tends to increase in isolated systems. This trend arises statistically from the large number of possible configurations. It reflects probability, not instability in physical law. Brownian motion demonstrates microscopic particle activity. When small particles are suspended in a fluid, they exhibit random motion. This motion arises from collisions with surrounding molecules. Although individual collisions are unpredictable, the overall behavior follows statistical laws. Albert Einstein analyzed Brownian motion mathematically, providing strong evidence for the existence of atoms. Experimental confirmation matched theoretical predictions closely. Brownian motion illustrates how microscopic dynamics produce observable macroscopic effects without violating deterministic laws. Chemical equilibrium reflects balanced forward and reverse reactions. In many chemical systems, reactions proceed in both directions simultaneously. At equilibrium, the rates of forward and reverse reactions are equal. Concentrations remain constant over time. This balance arises from energy minimization and statistical behavior. Equilibrium constants can be calculated from thermodynamic principles. Even at equilibrium, microscopic reactions continue. Molecules constantly rearrange. The stability observed at larger scales results from balanced dynamic processes. DNA structure depends on atomic bonding principles. The double helix of DNA arises from covalent bonds within sugar phosphate backbones and hydrogen bonds between complementary base pairs. The geometry is determined by bond angles and molecular interactions. The pairing between adenine and thymine, and between cytosine and guanine, follows specific hydrogen bonding patterns. These patterns ensure accurate replication. Although biologically complex, the structure of DNA rests entirely on atomic interactions, governed by electromagnetic forces and quantum mechanics. Proteins fold according to energy minimization. A protein is a chain of amino acids linked by covalent bonds. The sequence of amino acids determines how the chain folds into a three-dimensional structure. Folding occurs because certain configurations minimize free energy. Hydrogen bonds, hydrophobic interactions, and ionic attractions stabilize specific shapes. The function of enzymes, structural proteins, and signaling molecules depends on this precise folding. Yet, the folding process obeys the same physical laws that govern simpler molecules. Water's properties arise from hydrogen bonding networks. Each water molecule can form hydrogen bonds with neighboring molecules. These bonds create a dynamic network that influences density, surface tension, and heat capacity. Water expands upon freezing because hydrogen bonding arranges molecules into an open lattice. This property allows ice to float on liquid water. The unusual characteristics of water are fully explained by molecular geometry and intermolecular forces. No additional principles are required. Chemical kinetics describes reaction rates mathematically. The rate at which a reaction proceeds depends on factors such as temperature and concentration. Arrhenius equations relate temperature to reaction rate through activation energy. Molecules must collide with sufficient energy and proper orientation to react. The distribution of molecular energies determines how many collisions meet this condition. Reaction rate laws can be measured experimentally and predicted theoretically. The consistency between experiment and theory demonstrates the reliability of microscopic descriptions. Electromagnetic radiation spans a continuous spectrum. Light is part of a broader electromagnetic spectrum that includes radio waves, microwaves, infrared, visible light, ultraviolet, X-rays, and gamma rays. These differ only in wavelength and frequency. All electromagnetic waves propagate according to Maxwell's equations. These equations describe how electric and magnetic fields interact and propagate through space. At the microscopic level, photons interact with electrons. The absorption or emission of photons corresponds to transitions between quantized energy states. Solid matter resists compression due to electron repulsion. When two solid objects are pressed together, their electron clouds interact. The Pauli exclusion principle prevents electrons from occupying identical states. Electromagnetic repulsion increases rapidly at short distances. This resistance produces the sensation of solidity. The nuclei rarely approach closely. Instead, electron distributions create effective barriers. Thus, the apparent firmness of matter arises from quantum mechanical principles governing electrons. Superconductivity occurs when electrons form correlated pairs. At very low temperatures, certain materials exhibit zero electrical resistance. In these materials, electrons pair into collective states known as Cooper pairs. These pairs move coherently through the lattice without scattering. The formation of Cooper pairs arises from interactions between electrons and lattice vibrations. Superconductivity is described through quantum theory and confirmed experimentally. It represents a collective quantum phenomenon emerging from microscopic interactions. Microscopic laws scale upward through collective behavior. Individual atomic interactions combine to produce bulk material properties. Elasticity, conductivity, and chemical reactivity arise from aggregated microscopic processes. Although single particle behavior involves probability distributions, large numbers produce stable averages. Statistical laws smooth out fluctuations. The macroscopic world appears stable because microscopic interactions are consistent, and because immense numbers of particles average out variation. The microscopic framework remains coherent across scales. From quarks bound by the strong force to molecules forming biological systems, each layer builds upon the previous one. No separate physical laws are introduced at larger scales. The same forces operate throughout. The Standard Model describes elementary particles. Quantum mechanics governs atomic structure. Electromagnetism shapes chemistry. Statistical mechanics connects particle motion to thermodynamics. These layers interconnect without contradiction. The stability of matter reflects this coherent structure. The microscopic world operates continuously and without interruption. At every moment, electrons occupy orbitals. Photons propagate. Atomic nuclei remain bound by strong forces. Molecules vibrate and rotate. These processes proceed according to mathematical laws confirmed through repeated experiment. They do not depend on observation to continue. Beneath the visible world, the microscopic structure persists. Its rules remain stable. Its behavior remains consistent. And its quiet activity forms the enduring foundation of all material existence. Quantum chromodynamics describes how quarks interact through color charge. Quarks possess a property known as color charge, which is unrelated to visual color. This property determines how quarks interact via the strong force. There are 3 types of color charge, commonly labeled red, green, and blue for convenience. The strong force acts between quarks through the exchange of gluons. Gluons themselves carry color charge, allowing them to interact with each other as well as with quarks. This self-interaction distinguishes the strong force from electromagnetism. The mathematical framework of quantum chromodynamics predicts how quarks behave at high energies. Experimental results from particle accelerators confirm these predictions. At ordinary energies, quarks remain confined within composite particles, such as protons and neutrons. Quark confinement prevents isolated quarks from being observed. When quarks are pulled apart, the strong force between them increases rather than decreases. Energy supplied to separate them eventually produces new quark-antiquark pairs instead of isolating a single quark. This behavior ensures that quarks are always found in combinations forming color-neutral particles. Protons and neutrons are examples of such combinations. The principle of confinement has been supported by extensive experimental evidence. Despite decades of searching, no free quark has been observed under normal conditions. Hadrons are composite particles formed from quarks. Particles composed of 3 quarks are known as baryons. Protons and neutrons are baryons. Particles composed of a quark and an antiquark are known as mesons. The internal structure of hadrons influences nuclear interactions. Mesons can mediate forces between nucleons inside atomic nuclei. These interactions contribute to nuclear binding. The classification of hadrons follows systematic patterns predicted by symmetry principles. These patterns were identified before quarks were directly confirmed in high-energy experiments. The atomic nucleus is stabilized by the residual strong force. Although quarks are bound tightly inside protons and neutrons, a weaker residual effect of the strong force acts between nucleons. This residual interaction binds protons and neutrons together in the nucleus. The residual strong force is powerful at very short distances. It overcomes the electromagnetic repulsion between positively charged protons. However, it decreases rapidly beyond nuclear distances. The balance between strong attraction and electromagnetic repulsion determines nuclear stability. Nuclei with certain combinations of protons and neutrons are stable. Others undergo radioactive decay. Radioactive decay results from unstable nuclear configurations. Some nuclei possess excess energy due to imbalanced forces. They can transform into more stable configurations through decay processes. Alpha decay, beta decay, and gamma emission are common modes. In alpha decay, a nucleus emits a helium nucleus composed of 2 protons and 2 neutrons. In beta decay, the weak force converts a neutron into a proton, or vice versa. Gamma emission releases excess energy as high-energy photons. These decay processes follow statistical laws. Each unstable nucleus has a characteristic half-life. The predictability of decay rates allows precise measurement and practical applications in medicine and geology. Isotopes differ in nuclear stability. Atoms of the same element may contain different numbers of neutrons. Some isotopes are stable, others are radioactive. Stability depends on the balance of nuclear forces. For lighter elements, stable nuclei often have roughly equal numbers of protons and neutrons. For heavier elements, additional neutrons are required to offset increasing proton repulsion. The study of isotopes provides insight into nuclear structure. It also enables radiometric dating techniques that determine the age of rocks and archaeological materials. Nuclear fission splits heavy nuclei into lighter fragments. In certain heavy elements, such as uranium, the nucleus can split into 2 smaller nuclei when struck by a neutron. This process releases energy and additional neutrons. The released neutrons can trigger further fission events. If controlled, this chain reaction generates steady power in nuclear reactors. If uncontrolled, it can produce explosive energy release. Fission is explained by nuclear binding energy differences. The total binding energy per nucleon is higher in medium-weight nuclei than in very heavy ones, making fission energetically favorable. Binding energy determines nuclear stability. Binding energy represents the energy required to separate a nucleus into individual protons and neutrons. It arises from the strong force holding nucleons together. The binding energy per nucleon varies with atomic number. It peaks around elements such as iron and nickel. This explains why both fusion of light elements and fission of heavy elements can release energy. Precise measurements of nuclear masses confirm these energy relationships. The mass differences correspond exactly to predicted energy values. The electromagnetic force is described by Maxwell's equations. Maxwell's equations unify electricity and magnetism into a single theoretical framework. They describe how electric and magnetic fields are generated and how they propagate. At the microscopic level, charged particles create electric fields. Moving charges generate magnetic fields. These fields influence other charges, producing forces. Maxwell's equations predict electromagnetic waves traveling at the speed of light. This theoretical prediction was confirmed experimentally and forms the basis for understanding light as an electromagnetic phenomenon. Quantum electrodynamics refines electromagnetic theory. Quantum electrodynamics combines quantum mechanics with special relativity to describe interactions between charged particles and photons. It provides extremely accurate predictions of measurable quantities. For example, the magnetic moment of the electron has been calculated and measured to extraordinary precision. The agreement between theory and experiment extends to many decimal places. This precision demonstrates the reliability of quantum field theory as a description of microscopic interactions. Special relativity governs high-speed particle behavior. When particles approach the speed of light, classical mechanics becomes insufficient. Special relativity describes how time and space behave at high velocities. Relativistic equations modify energy and momentum relationships. These corrections are essential in particle accelerators, where particles routinely travel near light speed. Relativity and quantum mechanics are combined in quantum field theory. This integration ensures that microscopic descriptions remain consistent with fundamental spacetime principles. Symmetry principles guide particle classification. Many features of the Standard Model arise from symmetry considerations. Gauge symmetries determine the allowed interactions between particles. These symmetries are expressed mathematically through group theory. The electromagnetic, weak, and strong forces each correspond to specific symmetry groups. The presence of symmetry does not imply simplicity. It reflects underlying consistency. The mathematical structure constrains how particles can interact, producing predictive power. Spontaneous symmetry breaking gives rise to distinct particle properties. In certain physical systems, the underlying equations possess symmetry, yet the observed state does not. This phenomenon is known as spontaneous symmetry breaking. The Higgs mechanism is an example. Although the fundamental equations are symmetric, the Higgs field adopts a specific value throughout space. This choice leads to distinct particle masses. Spontaneous symmetry breaking explains why some forces have short range and others long range. It plays a central role in the Standard Model. Vacuum is not entirely empty in quantum field theory. In quantum theory, the lowest energy state of a field is not simply absence. Fields possess fluctuations even in their ground state. These fluctuations are predicted mathematically and observed indirectly. For example, the Casimir effect demonstrates measurable forces arising from vacuum fluctuations between closely spaced plates. These phenomena do not destabilize matter. They represent subtle aspects of quantum fields operating within strict mathematical limits. The speed of light sets a fundamental limit on information transfer. No signal or causal influence can propagate faster than light in vacuum. This limit is embedded in the structure of relativity. Quantum entanglement does not violate this limit. Although correlated measurement outcomes occur, no usable information travels faster than light. The speed limit ensures consistent causal structure in physical law. It maintains coherence across spacetime descriptions. Entanglement describes correlated quantum states. When particles interact, their quantum states can become linked. The overall system is described by a single combined wave function. Measurements on one particle influence the correlated probabilities of the other. Entanglement has been demonstrated experimentally in numerous tests. The statistical correlations match quantum mechanical predictions. Although entanglement defies classical intuition, it remains fully consistent with quantum theory and relativity. It does not introduce unpredictability at macroscopic scales. Macroscopic objects obey classical laws as emergent approximations. At large scales, quantum effects average out. The behavior of everyday objects can be described accurately using classical mechanics. This transition from quantum to classical behavior arises from decoherence. Interactions with the environment suppress observable interference effects. The emergence of classical behavior does not replace quantum mechanics. It represents an effective description, valid when dealing with large numbers of particles. Decoherence explains the apparent definiteness of measurement outcomes. When a quantum system interacts with its surroundings, its superposition states become entangled with environmental degrees of freedom. This interaction rapidly suppresses interference effects. As a result, macroscopic outcomes appear definite. The underlying quantum description remains intact, but certain correlations become effectively inaccessible. Decoherence provides a mechanism linking quantum probability to classical experience without altering fundamental equations. Microscopic interactions shape chemical periodicity. The repeating trends across the periodic table arise from electron shell filling patterns. Ionization energy, atomic radius, and electronegativity vary predictably. These trends influence how elements react. Metals tend to lose electrons. Non-metals tend to gain them. Noble gases possess filled shells and exhibit minimal reactivity. Periodic behavior demonstrates how quantum mechanics structures chemical diversity in a systematic manner. Chemical diversity emerges from limited building blocks. All matter is composed primarily of a relatively small number of elements. Carbon, hydrogen, oxygen, and nitrogen dominate biological systems, yet their combinations produce vast molecular diversity. This diversity arises from bonding versatility, especially of carbon. Carbon forms 4 covalent bonds, allowing chains, rings, and complex networks. The complexity of organic chemistry does not introduce new physical laws. It represents combinatorial richness built upon consistent atomic interactions. Surface phenomena arise from atomic scale interactions. At surfaces, atoms experience different bonding environments than in bulk material. This leads to phenomena such as surface tension, adsorption, and catalysis. Catalytic reactions occur when molecules bind temporarily to surfaces. The surface lowers activation energy by stabilizing intermediate states. Surface chemistry underlies processes ranging from industrial synthesis to biological enzyme function. The principles remain rooted in electron interactions and energy minimization. Nanostructures exhibit size-dependent properties. When materials are reduced to nanometer scales, quantum confinement effects become significant. Electron energy levels shift due to restricted spatial dimensions. Quantum dots are examples of nanostructures whose optical properties depend on size. Smaller dots emit higher energy light. Larger dots emit lower energy light. These size-dependent properties follow from boundary conditions applied to electron wave functions. They are predictable and measurable. The microscopic world remains governed by consistent mathematical laws. Across scales from quarks to nanostructures, interactions are described by equations tested experimentally. Each layer builds upon the previous one without contradiction. The forces remain the same. Conservation laws remain intact. Symmetry principles continue to constrain interactions. The quiet activity of particles, fields, and bonds proceeds continuously. Beneath every material surface, beneath every living cell, microscopic processes maintain their steady structure. As we continue further, we will move toward how collective microscopic behavior shapes materials, biological systems, and the stable physical environment experienced at human scales. The foundation remains precise, the framework remains stable, and the microscopic world continues its constant measured activity beneath everything you know. Phase transitions occur when collective microscopic behavior reorganizes. A phase transition happens when a material changes from one state to another, such as from solid to liquid or liquid to gas. At the microscopic level, this reflects a change in how particles are arranged and how they move. In a solid, atoms occupy fixed lattice positions and vibrate around equilibrium points. In a liquid, atoms remain close but can move past one another. In a gas, particles move independently across large distances. The transition between phases depends on temperature and pressure. These macroscopic variables correspond to microscopic energy and particle spacing. The mathematical treatment of phase transitions uses statistical mechanics to connect individual particle behavior with collective change. Melting occurs when thermal motion overcomes lattice binding. In a crystalline solid, atoms are held in place by bonding forces. As temperature increases, atomic vibrations increase in amplitude. At the melting point, vibrational energy becomes sufficient to disrupt the fixed lattice arrangement. The structure does not disappear entirely. Short-range interactions remain. However, long-range order is lost. Atoms can now move relative to each other while remaining close. The melting temperature depends on bond strength and lattice structure. Stronger bonds generally require more energy to overcome, resulting in higher melting points. Boiling reflects the formation of vapor within a liquid. As temperature rises, some molecules in a liquid acquire enough kinetic energy to escape into the gas phase. At the boiling point, vapor pressure equals external pressure, allowing bubbles to form throughout the liquid. The energy required for boiling includes breaking intermolecular interactions. In water, hydrogen bonds must be disrupted. This requires substantial energy compared to similar-sized molecules without hydrogen bonding. Boiling illustrates how microscopic interactions determine macroscopic properties. The phase boundary emerges from collective molecular motion governed by energy distributions. Critical points represent the end of distinct liquid and gas phases. At a specific temperature and pressure, known as the critical point, the distinction between liquid and gas disappears. Density differences vanish. The material becomes a supercritical fluid. Near the critical point, fluctuations occur across multiple length scales. Correlations between particle positions extend over large distances compared to typical molecular spacing. Theoretical descriptions of critical phenomena use scaling laws and renormalization methods. These frameworks describe how microscopic interactions give rise to universal behavior near transition points. Thermal expansion results from asymmetric potential energy curves. Atoms in a solid interact through potential energy functions that are not perfectly symmetric. As temperature increases, atoms spend more time at slightly larger separations than at smaller ones. This asymmetry leads to an increase in average atomic spacing. As a result, the material expands. The expansion coefficient depends on bonding strength and crystal structure. Thermal expansion is therefore a direct consequence of interatomic potential shapes derived from electromagnetic interactions. Elasticity arises from restoring forces between atoms. When a solid is deformed slightly, atoms are displaced from equilibrium positions. Interatomic forces act to restore original spacing. If deformation remains small, these forces follow approximately linear relationships. This behavior leads to Hooke's law, which describes proportionality between applied force and displacement. The proportionality constant depends on bond stiffness and atomic arrangement. Elastic behavior is thus a macroscopic expression of microscopic electromagnetic forces between atoms. Plastic deformation involves permanent rearrangement of atomic structure. When stress exceeds a certain threshold, atoms shift into new configurations. Dislocations move through the crystal lattice. These defects allow layers of atoms to slide past one another. Plasticity does not violate bonding principles. Instead, it involves local rearrangements of bonds into new stable positions. The study of dislocations and crystal defects connects atomic scale interactions with engineering properties of materials. Diffusion describes particle motion driven by concentration gradients. Atoms and molecules move randomly due to thermal motion. When concentration differences exist, this random motion produces net transport from high to low concentration. Fick's laws describe diffusion mathematically. The rate depends on temperature and on the medium through which particles move. Diffusion underlies processes such as alloy formation, gas exchange in lungs, and chemical mixing. The mechanism remains rooted in molecular motion, governed by statistical distributions. Viscosity reflects resistance to relative motion between layers. In fluids, molecules transfer momentum between adjacent layers. This momentum exchange resists flow. The microscopic origin lies in intermolecular interactions and molecular collisions. Stronger interactions generally increase viscosity. Temperature influences viscosity by altering molecular motion and interaction times. The equations of fluid dynamics incorporate viscosity as a parameter. Its value ultimately derives from atomic and molecular behavior. Heat conduction results from energy transfer between particles. In solids, energy moves through lattice vibrations and through mobile electrons in metals. In gases and liquids, energy transfer occurs through molecular collisions. Fourier's law describes heat flow proportional to temperature gradients. The thermal conductivity of a material depends on how efficiently microscopic energy carriers propagate. Phonons, which are quantized lattice vibrations, play a central role in heat conduction in insulators. These quasi-particles emerge from collective atomic motion. Phonons represent collective vibrational modes of a lattice. In a crystal, atoms vibrate in coordinated patterns. These vibrations can be described as wave-like modes extending through the material. Quantum mechanically, these modes are quantized into phonons. Each phonon carries discrete energy. The distribution of phonons determines heat capacity and thermal conductivity. Phonon interactions explain temperature-dependent behavior of solids. At low temperatures, phonon populations decrease, altering material properties. Heat capacity reflects accessible microscopic energy states. The heat capacity of a material indicates how much energy is required to raise its temperature. At the microscopic level, this depends on available energy modes. In solids, vibrational modes contribute to heat capacity. In gases, translational and rotational modes are significant. Quantum effects modify heat capacity at low temperatures. Theoretical models, such as the Debye model, describe these behaviors. Experimental measurements confirm the predicted temperature dependence. Magnetism arises from electron spin and orbital motion. In atoms, electrons possess magnetic moments due to spin and orbital angular momentum. In many materials, these moments are randomly oriented and cancel out. In ferromagnetic materials, interactions between electron spins cause alignment over regions known as domains. This alignment produces net magnetization. Magnetic ordering depends on quantum exchange interactions. These interactions arise from the Pauli exclusion principle and Coulomb repulsion. The macroscopic magnetic field reflects coordinated microscopic spin alignment. Paramagnetism and diamagnetism reflect different microscopic responses. In paramagnetic materials, unpaired electron spins align weakly with an external magnetic field. In diamagnetic materials, induced currents oppose the applied field slightly. Both effects arise from electron motion in atomic orbitals. The strength of response depends on electronic structure. These magnetic behaviors demonstrate how quantum properties influence observable material characteristics. Electrical resistance results from electron scattering. In conductive materials, electrons move through a lattice of ions. Imperfections, lattice vibrations, and impurities scatter electrons, impeding motion. The degree of scattering determines electrical resistance. At higher temperatures, lattice vibrations increase, leading to greater scattering and higher resistance. Ohm's law describes the relationship between voltage, current, and resistance. The microscopic explanation lies in electron dynamics and interactions. Semiconductor band structure determines electronic devices. In semiconductors, energy bands define allowed and forbidden energy ranges for electrons. The band gap separates filled valence bands from empty conduction bands. Doping introduces additional energy levels, creating excess electrons or holes. These charge carriers enable controlled conductivity. Diodes and transistors rely on manipulating these carriers through electric fields. The behavior of modern electronics depends on quantum mechanical band theory applied at microscopic scales. Photovoltaic cells convert light into electrical energy. When photons strike a semiconductor, they can excite electrons across the band gap. This creates electron-hole pairs. An internal electric field separates these charges, generating current. The efficiency of this process depends on band gap size, material purity, and device design. Solar energy conversion is therefore an application of quantum interactions between photons and electrons within structured materials. Biological membranes depend on molecular self-assembly. Phospholipid molecules contain hydrophilic heads and hydrophobic tails. In aqueous environments, they spontaneously arrange into bilayers. This arrangement minimizes free energy. Hydrophobic tails cluster away from water, while hydrophilic heads interact with it. Membrane structure arises from intermolecular forces and entropy considerations. It provides a stable boundary for cells while remaining dynamic at the molecular level. Enzymes accelerate reactions by stabilizing transition states. An enzyme binds substrates in specific orientations. It lowers activation energy by stabilizing intermediate configurations. The catalytic effect arises from precise atomic interactions within the active site. Hydrogen bonds, electrostatic forces, and induced fit mechanisms contribute. Despite biological complexity, enzyme function is governed by the same chemical bonding principles that operate in simpler reactions. Metabolism consists of interconnected chemical pathways. Cells carry out sequences of reactions that transform molecules step by step. Each step is catalyzed by specific enzymes. Energy transfer within cells often involves molecules such as ATP. The hydrolysis of ATP releases energy stored in chemical bonds. These biochemical processes reflect energy redistribution governed by thermodynamics and molecular structure. The microscopic world underlies biological stability. Cells maintain order by regulating chemical reactions and energy flow. Ion gradients across membranes depend on controlled transport proteins. Genetic information is stored in molecular sequences. Replication and transcription rely on complementary base pairing. Every biological function depends on atomic interactions. The continuity of life reflects the continuity of microscopic physical law. The stability of matter extends from particles to organisms. Quarks form nucleons. Nucleons form nuclei. Nuclei and electrons form atoms. Atoms bond into molecules. Molecules assemble into materials and living systems. At each level, new structures emerge from interactions at the level below. Yet, the underlying forces remain the same. The microscopic world does not fluctuate unpredictably. It operates through consistent mathematical relationships confirmed by experiment. Across all scales we have explored, from quantum fields to biological membranes, the same principles persist. Forces balance. Energy is conserved. Probability distributions remain well defined. Beneath every surface, beneath every structure, microscopic processes continue steadily. Electrons occupy orbitals. Bonds vibrate. Particles interact through fields. The structure is stable. The rules are constant. And the microscopic foundation of matter continues its quiet, uninterrupted activity beneath the visible world. Chemical potential governs the movement of particles between regions. Chemical potential represents the change in a system's energy when an additional particle is introduced. Particles tend to move from regions of higher chemical potential to regions of lower chemical potential. This principle explains diffusion, osmosis, and phase equilibrium. In solutions, solvent molecules move in response to differences in chemical potential across membranes. The concept links microscopic particle statistics with macroscopic flow. It arises from thermodynamic analysis grounded in molecular behavior and energy minimization. Osmosis results from differences in solute concentration. When a semi-permeable membrane separates two solutions of different solute concentrations, solvent molecules move toward the higher solute concentration. This movement continues until chemical potentials equalize. The resulting pressure difference is known as osmotic pressure. Osmosis is essential in biological systems. Cells regulate water balance through membrane transport mechanisms that depend on molecular interactions and concentration gradients. Ion channels regulate electrical behavior in cells. Cell membranes contain protein structures that allow selective passage of ions. These channels open and close in response to voltage or chemical signals. Ion movement across membranes generates electrical potentials. Nerve impulses result from coordinated opening and closing of sodium and potassium channels. Although biological in function, ion channel behavior is determined by electrostatic forces and concentration gradients at the atomic scale. Electrochemical gradients combine electrical and chemical forces. Charged particles in solution experience forces from electric fields and from concentration differences. The combined effect is described by electrochemical potential. Cells use electrochemical gradients to drive transport processes. For example, proton gradients across mitochondrial membranes power ATP synthesis. These gradients arise from controlled molecular transport and are maintained through energy input from metabolism. ATP synthesis involves rotational molecular machinery. A TP synthase is a protein complex embedded in membranes. It uses proton flow down an electrochemical gradient to drive mechanical rotation. This rotation changes the shape of catalytic sites, enabling the formation of ATP from ADP and phosphate. The mechanism reflects energy conversion at molecular scale. Proton movement, electrostatic interactions, and conformational changes combine to produce biochemical energy storage. Mechanical properties of materials reflect atomic bonding patterns. Materials with strong directional covalent bonds tend to be hard and brittle. Metals with delocalized electron bonding tend to be malleable and ductile. The arrangement of atoms in crystal structures influences slip planes and fracture behavior. Engineering properties emerge from atomic scale bonding geometry and electron distribution. Amorphous solids lack long-range order. Unlike crystalline materials, amorphous solids, such as glass, do not possess repeating lattice structures. Atoms are arranged irregularly, but remain bound by chemical forces. This lack of long-range order influences optical and mechanical properties. Glass can be transparent because it lacks periodic structures that scatter visible light strongly. The distinction between crystalline and amorphous states reflects differences in atomic arrangement, not differences in fundamental forces. Surface tension arises from intermolecular attraction, imbalance. Molecules at the surface of a liquid experience fewer neighboring interactions than those in the bulk. This imbalance creates a net inward force. The result is surface tension, which causes liquids to minimize surface area. Droplets adopt spherical shapes in absence of external forces. Surface tension is a direct consequence of intermolecular electromagnetic interactions and energy minimization. Capillary action depends on adhesive and cohesive forces. When a liquid contacts a narrow tube, adhesive forces between liquid and tube walls can exceed cohesive forces within the liquid. If adhesion dominates, the liquid rises in the tube. If cohesion dominates, the liquid level depresses. This behavior arises from molecular interactions and surface energy considerations at microscopic interfaces. Crystallization occurs through nucleation and growth. When a liquid cools below its freezing point, small clusters of ordered atoms may form. If these clusters exceed a critical size, they become stable nuclei for crystal growth. Atoms attach to the growing crystal lattice in specific orientations determined by bonding geometry. The rate of crystallization depends on temperature, diffusion rates, and energy barriers. These factors are analyzed through thermodynamic and kinetic models. Supersaturation enables controlled crystal formation. A solution can hold more dissolved material than equilibrium permits at a given temperature. This metastable state is called supersaturation. If a nucleation site appears, rapid crystallization can occur. The process releases energy and restores equilibrium. Supersaturation demonstrates how microscopic energy barriers influence macroscopic stability. Colloids consist of dispersed microscopic particles. Colloidal systems contain particles larger than molecules, but small enough to remain suspended. Brownian motion helps prevent sedimentation. Electrostatic repulsion, or steric hindrance, stabilizes colloids by preventing aggregation. The stability of colloids depends on balance between attractive and repulsive forces at microscopic scales. Polymers are long chains of repeating molecular units. Polymer chains consist of repeating monomer units linked by covalent bonds. Their mechanical properties depend on chain length, cross-linking, and intermolecular interactions. Flexible polymers can entangle, creating viscoelastic behavior. Cross-linked polymers form more rigid networks. Polymer behavior is described through statistical models of chain conformations and intermolecular forces. Glass transition reflects gradual molecular mobility change. In polymers and amorphous solids, the glass transition marks a temperature range where molecular motion becomes significantly restricted. Unlike melting, this transition does not involve a sharp structural change. Instead, molecular mobility decreases progressively. The glass transition temperature depends on molecular structure and intermolecular interactions. Liquid crystals exhibit partial ordering. Liquid crystals possess properties between liquids and solids. Molecules maintain orientational order while retaining fluidity. Their behavior arises from anisotropic molecular shapes and intermolecular forces. Liquid crystal displays exploit changes in molecular orientation under electric fields, linking microscopic alignment to visible images. Acids and bases involve proton transfer reactions. An acid donates a proton. A base accepts a proton. In aqueous solutions, these transfers form hydronium and hydroxide ions. The strength of acids and bases depends on equilibrium constants determined by bond strength and solvation energy. Acid-base chemistry reflects proton interactions governed by electromagnetic forces. Redox reactions involve electron transfer. Oxidation corresponds to loss of electrons. Reduction corresponds to gain of electrons. Electron transfer reactions drive processes such as combustion, corrosion, and cellular respiration. The driving force depends on differences in electron energy levels and electrochemical potentials. Corrosion results from electrochemical reactions at surfaces. In metals exposed to oxygen and moisture, redox reactions can convert metal atoms into ions. This process involves electron flow and formation of oxide layers. The rate depends on environmental conditions and material composition. Corrosion illustrates how microscopic electron transfer leads to macroscopic material degradation. Catalysis reduces activation energy barriers. A catalyst provides an alternative reaction pathway with lower activation energy. It does not alter overall thermodynamics. Surface catalysts bind reactants transiently, stabilizing intermediate states. Catalytic efficiency arises from precise molecular interactions at atomic scale. Photochemistry involves light-induced electronic transitions. When molecules absorb photons, electrons can be promoted to higher energy states. These excited states may undergo chemical reactions different from ground state reactions. Photosynthesis relies on photochemical processes to convert light energy into chemical energy. Photosynthesis stores solar energy in chemical bonds. In chloroplasts, light absorption initiates electron transfer chains. These chains generate proton gradients used to synthesize ATP. Carbon dioxide is reduced to form carbohydrates through enzyme-catalyzed pathways. The entire process depends on electron excitation, redox chemistry, and energy coupling mechanisms. Respiration releases stored chemical energy. In cells, carbohydrates are oxidized through a series of reactions. Electrons are transferred to oxygen, forming water. Energy released during these reactions drives ATP synthesis. Respiration demonstrates how controlled electron transfer supports life processes. Homeostasis depends on molecular regulation. Cells maintain stable internal conditions by controlling ion concentrations, pH, and temperature. Transport proteins and feedback mechanisms adjust molecular flows. This regulation reflects coordinated chemical reactions governed by microscopic physical laws. The microscopic foundation remains consistent across systems. Whether in a crystalline solid, a flowing fluid, or a living cell, interactions arise from the same forces. Electromagnetism shapes bonding and molecular structure. The strong force stabilizes nuclei. Quantum mechanics governs particle states. Each layer of complexity emerges from stable underlying principles. The microscopic world continues its steady activity. Particles interact through fields. Molecules vibrate. Ions move along gradients. Bonds form and break in measured sequences. No part of this structure depends on perception. It operates according to equations verified repeatedly. Beneath the surface of every object and organism, the same processes persist. The structure is maintained. The forces remain balanced. The interactions follow established laws. And the microscopic world continues, quietly and reliably, forming the stable foundation beneath all visible matter. Atomic nuclei remain bound by the strong nuclear interaction under ordinary conditions. Within every stable atom, protons and neutrons are held together by forces that operate over extremely short distances. These forces are strong enough to overcome the electrical repulsion between positively charged protons. The balance between attractive nuclear interactions and repulsive electrical forces determines whether a nucleus remains intact. For most elements found on Earth, this balance is stable over immense spans of time. Nuclei do not spontaneously rearrange without specific conditions being met. Their structure is resilient at everyday temperatures and pressures. This nuclear stability forms the basis for the persistence of matter in its current form. Because nuclear forces act at such short range, they do not interfere with chemical behavior beyond the scale of the nucleus. The stability of nuclei ensures that atoms retain their elemental identity unless subjected to extreme environments. Electron distributions around nuclei settle into stable energy configurations. Electrons occupy allowed energy states determined by the electromagnetic attraction of the nucleus and the mathematical constraints of quantum mechanics. These states are not arbitrary. They represent solutions that minimize energy while satisfying physical laws. Unless energy is added or removed through interaction, electrons remain in these states. They do not collapse inward or drift outward without cause. The quantist nature of their energy prevents gradual instability. This stability ensures that atoms retain consistent chemical properties. The arrangement of electrons defines how atoms bond and how they respond to external fields. As long as energy conditions remain moderate, electron configurations remain steady. Chemical bonds persist because they correspond to lower energy arrangements. When atoms share or transfer electrons, the resulting configuration often has lower total energy than the separate atoms. This energy reduction stabilizes the bonded state. Breaking a bond requires input of energy sufficient to overcome this stability. At ordinary temperatures, many bonds remain intact for long periods. Molecular structures maintain their form because random thermal motion is insufficient to disrupt all bonding simultaneously. The strength and geometry of bonds determine molecular durability. Complex molecules, including those in living systems, remain structured because their bonding patterns are energetically favorable. Thermal motion remains bounded by energy constraints. Atoms and molecules vibrate and move continuously. Their motion reflects thermal energy distributed statistically. However, this motion is limited by the strength of the interactions between them. In solids, vibrations occur around equilibrium positions. In liquids, motion allows rearrangement without complete separation. In gases, motion increases but remains governed by collisions and energy conservation. Temperature influences motion, but within ordinary ranges, it does not disrupt fundamental structure. Thermal activity is continuous, yet contained within predictable limits. Conservation laws maintain consistency in every microscopic interaction. Energy, momentum, and electric charge remain conserved in all observed processes. When particles interact, these quantities are redistributed, but not lost or created spontaneously. These conservation principles arise from the symmetry of physical laws. They constrain what transitions are allowed and prevent arbitrary change. Because of conservation, interactions remain structured. Outcomes follow defined pathways. This consistency extends from subatomic interactions to chemical reactions and material behavior. Statistical behavior produces macroscopic stability from microscopic motion. Individual particles move and interact in ways described by probability distributions. Yet, when vast numbers of particles are involved, average behavior becomes highly predictable. Fluctuations at small scales do not destabilize large systems. Instead, they average out, producing steady temperature, pressure, and structural integrity. The visible stability of objects around you reflects the combined effect of countless microscopic interactions proceeding according to consistent rules. The microscopic framework continues regardless of observation. Atoms do not require attention to remain bound. Electrons do not need to be measured to occupy their states. Forces act continuously, whether or not they are noticed. Within every solid surface, atomic lattices remain arranged. Within every liquid, molecules continue to move and interact. Within every gas, particles travel and collide. These processes unfold according to equations tested and confirmed. They proceed without urgency and without interruption. Even as you rest, nuclei remain intact. Electrons continue to occupy stable regions around them. Bonds hold molecules together. Thermal motion continues within limits set by energy. Nothing at the microscopic scale requires intervention. The structure of matter does not depend on awareness. Forces balance as they have balanced for billions of years. Atoms maintain their spacing. Particles exchange energy in small, measured amounts. Molecules vibrate gently within their bonds. Fields extend quietly through space. Interactions occur and conclude in accordance with conservation laws. Across every surface and within every cell, this steady activity persists. There is no instability spreading outward, no hidden disorder advancing, only constant, governed interaction. Electrons remain in their allowed states. Nuclei retain their composition. Bonds continue to hold. Heat flows gradually where gradients exist. Motion remains bounded. Matter stays organized. The microscopic world continues its work quietly. Particles remain in balance. Atoms hold their form. Forces continue steadily. Energy redistributes in small exchanges. Nothing at this scale calls for attention. Nothing needs correction. The structure beneath you is stable. The air around you is structured. The materials supporting you are arranged, atom by atom. All of it persists. You do not need to follow the details any further. The interactions will continue without you tracking them. The equations remain satisfied. The forces remain balanced. Atoms keep their spacing. Molecules keep their bonds. Particles continue to interact predictably. The microscopic world does not pause. It does not rush. It simply proceeds. And as it proceeds, steadily and reliably, you can allow your thoughts to slow. The structure holds. The forces remain in quiet balance. Atoms maintain their form. Particles remain in motion within stable limits. Everything continues as it should. You can rest. You can let the details fade. The microscopic world will continue its calm, constant activity. Particles remain in balance. Atoms hold their form. Forces continue quietly. You can sleep. Good night.